The straight line analogy suggests a construction of reality in one dimension of a straight line. This one-dimension construction of reality could precede the 2 and 3 dimensions construction of reality, or they all could happen to exist at the same time, or they could have different space-time parameters. This straight line is an energy configuration. Information is encoded and scrambled on this straight line, which would require balancing properties to maintain its straightness, geometry, compactness, and dimensionality properties. This would be achieved by a balancing force. Some of the properties or characteristics of the balancing force would be repetitive, continuous, descriptive, unlimited, unbreakable, reproducible, and duality. The balancing force could be the main force behind some of the fundamental constants of our universe. The cosmological constant could be an example that will be presented shortly in this video. The main mechanism of how the balancing force would operate is likely to be resonance. The balancing force and the cosmological constant. An example of the balancing operation of the B force could be the cosmological constant. From the perspective of quantum field theory, every point in space is represented by a quantum oscillator, one for each elementary particle type. Higher energy oscillations represent the presence of real particles. However, even the lowest possible energy oscillation, the one corresponding to the absence of particles referred to as a vacuum state, has some energy. To satisfy the Heisenberg uncertainty principle, the vacuum state of any field oscillation E equals 1/2 hv, where v is the frequency of the oscillation. The theoretical value of zero-point energy suggested by quantum field theory is 10 to the power of 112 ergs per cubic centimeter. This estimate was first made by John Wheeler and Richard Feynman, who noted that one teacup of space with this energy density would contain enough energy to boil all of the oceans on the planet. The observed value of the vacuum energy density, the small value of the cosmological constant, is 10 to the power of -8 ergs per cubic centimeter. This discrepancy of 120 orders of magnitude is referred to as the vacuum catastrophe or the cosmological constant problem. If some fields can have extremely large positive zero-point energies, then perhaps others have extremely large negative zero-point energies that cancel them out. An extension of the standard model of particles called supersymmetry may partially allow this. It gives all particles a supersymmetric counterpart that may precisely cancel out the vacuum energy. Basic supersymmetry only allows us to cancel out photons down to the electroweak energy, which brings the predicted vacuum energy down to a mere 10 to the power of 47 ergs per cubic centimeter. For a while, theorists assumed that something like this must be happening, meaning the vacuum energy was really zero. In the late 90s, astronomers discovered that the expansion of the universe is accelerating in the way we would expect from non-zero vacuum energy. The observation of accelerating expansion allows us to measure the absolute density of vacuum energy. Quantum field theory can give us extremely high vacuum energy or vacuum energy of exactly zero if we assume the symmetry of positive and negative zero points between different fields. But a very small non-zero vacuum energy? That requires what is referred to as fine-tuning. Gigantic positive and gigantic negative zero-point energies cancel each other out down to a very tiny non-zero value. The balancing force could be a proposed solution. Earlier in this book, in the section The Physics Behind the Straight Line Analogy, we considered a value of 6.22404 times 10 to the -8 Kelvin to represent the Einstein temperature where all elements of the periodic table, when shattered to their elementary particles, form Bose-Einstein condensates, and there are no fluctuations. This could be referred to as the balanced state of the ISW's identity stem waves. Since 10 to the -8 is a value comparable to the vacuum energy density, we will consider that the vacuum energy density is the balanced state of the vacuum. The balancing force could be operating on the vacuum energy in some form of operation that needs to be and could be figured out to bring it to the balanced state of 10 to the -8. This operation aims not to cancel gigantic positive and negative energies out, but to bring them to a balanced state, which is estimated to require a value of 10 to the power of 120. The balancing force cannot have a value of 0. The operations of the balancing force are targeting to bring energies or fields to a balanced state. Every system or field has its non-zero balanced state, which could be calculated. The connection coefficients of the balancing force should allow the transformation of the balancing force to carry out the targeted operation, for example, bringing a field down to its balanced state. Physics is full of constants. These are values or properties for which there is no theoretical basis. They're only determined by measuring them. Some of these constants are things like the charge of the electron, the gravitational constant, Planck's constant, and others. If any of these numbers were different, our universe as we know it would not be the same. And we probably would not be here if that was the case. Why do these numbers have the values that they do? Why do these exact values make the universe suitable for us to be here? This is basically the core of the fine-tuning argument. It goes something like this. The constants of nature are statistically improbable. These constants are on a razor's edge such that even a slight deviation would likely result in no life as we know it in the universe. Some argue further and say that this fine-tuning is unlikely, that it could not have occurred by pure chance, that there must be an intelligent designer that set up the constants to enable life. Others reject this argument for various reasons. It is more or less like asking why we happen to live on a planet that happens to be at just the right temperature for liquid water to exist. That is a narrow edge. It is not as much of a knife edge as the cosmological constant. The answer is that on planets where there can't be water, there can't be life. So it's truly a very small fraction of planets at the right temperature for water to exist. Where do you live? In the only place we can live, where water exists. The same kind of picture, the universe is vast, very diverse, with many different environments and possibilities. Among these possibilities, in a few small pockets of the universe, the conditions are right for life, and that is where life exists. With planets, we know that there are many planets where a small number will have liquid water, and the vast majority will not. With the universe, we rely on theoretical ideas to say that there are different bubble or pocket universes, each one of which has different laws. Possibilities are like blueprints. They are blueprints for different kinds of universes. This could be analogous to the possibilities of life, as explained by Leonard Susskind. DNA is the blueprint for life. DNA has a vast number of ways of being rearranged, so there are many possibilities for life. But that in itself does not say that there is an enormous number of living creatures around. It took something to make those blueprints into actual houses or whatever it happens to be. Part of the story is cosmological, that the expansion of the universe, the inflation of the universe, the very rapid expansion that took place at very early times created a lot of quantum fluctuation, and that quantum fluctuation created patches of space with different properties. Those patches are sometimes called pocket universes, or sometimes called bubble universes. We live in one of them. That is the picture. There is mathematics that goes with it, which is sometimes referred to as multiverse. Leonard Susskind used the term landscape to describe it, where he mentioned that the background comes from biology, the landscape of biological designs, and it means all the possible ways you can put DNA together. It is a tremendously large number of possibilities describing life. Similarly, all the various possible ways you could put the elements of physics together to make different kinds of pocket universes, just as the number of ways that you can arrange a DNA molecule is enormous. You have a DNA molecule with 1 billion base pairs. You can rearrange them in a massive number of ways, and that is why there are so many different possibilities for life. Similarly, the number of different blueprints is enormous. An analogy that the science fiction writer Douglas Adams used is a sentient puddle. A puddle wakes up one morning after a night of rain and says, "This is an interesting hole I find myself in. It fits me rather well. It fits me perfectly. It must have been made to have me in it." As the sun rises, the water evaporates, the puddle keeps thinking that the hole was made to have him in it until he disappears. But there could be lots of holes with lots of sentient puddles with different dimensions of the hole. Similarly, if we change the constants analogous to the dimensions of the holes, it would be an alternate universe. But life as we know it then may be different, and we would continue to say in that alternate existence, this universe must have been made to have us in it. Our understanding of the universe is incomplete, and we know it is incomplete. We cannot yet explain dark matter, dark energy, the asymmetry of matter versus antimatter, and a host of other things. It is quite possible that future, more complete theories could answer some of these questions, and explain the theoretical basis for the constants being what they are. Einstein said that nature shows us only the tail of the lion, but there is no doubt the lion belongs with it, and we see the lion only as a louse sitting upon him would. It is possible we simply have not yet seen the lion that awaits at the end of the tale. Are constants of nature changing? Paul Dirac in 1937 speculated that physical constants such as the gravitational constant or the fine structure constant might be subject to change over time in the proportion of the age of the universe. This has been a work in progress and an ongoing area of research. In a paper published in the journal Science Advances, scientists from UNSW Sydney reported that 4 new measurements of light emitted from a quasar 13 billion light-years away reaffirm past studies that have measured tiny variations in the fine structure constant. UNSW science professor John Webb says, "We found a hint that that number of the fine structure constant was different in certain regions of the universe, not just as a function of time but actually also in direction in the universe, which is quite odd if it's correct, but that's what we found." The balancing force, along with the other imaginary complex forces proposed in the book The Big Defreeze of the Universe, could give a plausible explanation from a different perspective for the idea of fine-tuning. The thinking goes that the universe is in a balanced state rather than in a fine-tuned state. The balancing force drives this balanced state for a specific period and space to achieve particular conditions for different forms of life generation mechanisms. There would be another operating force here, which would be the retrieving force that would be working on retrieving this kind of ecosystem to its original state. This is yet another important differentiation between the balancing force and the retrieving force. This would be analogous to our sentient puddle mentioned earlier. The balancing force would be the reason for the dimensions and the equilibrium factors for our sentient puddle. And the retrieving force would be the evaporation of the water. Both forces could be measured and potentially tested and observed. The proposed mathematics and notations could be a tool to measure them and track their effects. Otherwise, a different mathematical framework could be used. For example, the proposed symmetry-breaking mechanism for the identity stem wave of helium I is we could be a potential explanation for why the speed of light and massless particles has its value. Let's talk about resonance for a little bit. Resonance? Classical resonance. Resonance is something where we have some variable and it varies periodically. The periodic variation usually requires that you drive the system. So, you first drive it, and then the system oscillates. You drive the system with a variable frequency, then you observe a peak. So, the phenomenon of resonance is that when you have something which can periodically vary, and when you drive it, you see a peaked response when driven with a variable frequency. Wolfgang Ketterle, the famous physicist and Nobel laureate, mentioned a very interesting quote during one of his lectures at MIT. Resonance is the language we talk to atoms with. Resonance at a certain frequency is finite damping. That would mean after the system is driven, the oscillation does not last for an infinite amount of time. And that implies that when we drive the system and look at the response as a function of frequency, there is a finite width for the driven system, and in many ways the damping time and the finite width are related by Fourier transform. Atomic physics is interested in every single possible aspect of this resonance: the shape of the curve, how it can be modified, what happens when we tie it strongly, what happens when we tie it weakly, etc. We usually characterize oscillators by the sharpness of the resonance. The sharpness of the resonance is the ratio of the beats of the resonance and the frequency or the inverse of it. So if you have an oscillator at a kilohertz and the resonance is 1 hertz wide, we say the resonance has a Q, a quality factor of 1,000. And that means you can observe 1,000 oscillations before the oscillation decays away. The Q factor explains how fast energy decays in an oscillating system. It compares the frequency at which a system oscillates to the rate at which it dissipates its energy. The sharpness of resonance, described by the Q factor, increases or decreases with an increase or decrease in damping. As the amplitude increases the sharpness of resonance, the Q factor decreases. Higher Q indicates a lower rate of energy loss, and the oscillations die out more slowly. A pendulum suspended from a high-quality bearing, oscillating in air, has a high Q, while a pendulum immersed in oil has a low one. Resonators with high-quality factors have low damping so that they ring or vibrate longer. The frequency of light is 10 to the power of 15 Hz. The wavelength is 300 nanometers. For example, the Q of the Earth's rotation fulfills all of our requirements for resonance and oscillations. It is a periodic phenomenon. It has a Q of 10 to the power of 7, so the precision of the rotation of the Earth is better than 1 part in a million. The quality factor Q for a pulsar star is 10 to the power of 10. If a resonance has a high quality factor, the more sensitive it will be to tiny little changes. A high-quality oscillator is a tool for discovery. The resonant frequency is the oscillation of a system at its natural or unforced resonance. Resonance occurs when a system is able to store and easily transfer energy between different storage modes, such as kinetic energy or potential energy, as you would find with a simple pendulum. Most systems have one resonant frequency and multiple harmonic frequencies that get progressively lower in amplitude as they move away from the center. Resonance describes the phenomenon of increased amplitude that occurs when the frequency of a periodically applied force, or a Fourier component of it, is equal or close to a natural frequency of the system on which it acts. When an oscillating force is applied at a resonant frequency of a dynamic system, the system will oscillate at a higher amplitude than when the same force is applied at other, non-resonant frequencies. Frequencies at which the response amplitude is a relative maximum are also known as resonant frequencies or resonance frequencies of the system. Small periodic forces that are near a resonant frequency of the system can produce large amplitude oscillations in the system due to the storage of vibrational energy. Resonance phenomena occur with all types of vibrations or waves, including resonance of quantum wave functions. The angle of intersection of a wave with its axis. The energy quality is based on the shape of the wave. When we say the shape of the wave, we are referring to the proportion of the wavelength to the amplitude, irrelevant of the single measurement of frequency or wavelength. This quality can also be expressed by the angle that the wave crosses the central axis. In other words, the relationship of the amplitude to the wavelength is the main factor determining the energy quality effect of the wave on its environment, which could also be expressed as in the form of the angle of intersection of the wave with its axis. This concept was mentioned in the book Back to a Future for Mankind by Ibrahim Karim, an architect who is a graduate of the Federal Institute of Technology, Zurich, Switzerland, and teaches at several universities. It was mentioned in a different context related to how biogeometry assesses the effect of a wave on the subtle energy systems of its surroundings due to the quality of shape of that wave. Biogeometry is using the energy principles of shape to qualitatively balance biological energy systems and harmonize their interactions with the environment. At least this is how Ibrahim Karim explains it. It is worth mentioning that the concepts of biogeometry are neither widely recognized nor widely accepted. However, here we just want to discuss the idea of the angle of intersection of a wave with its axis within the context of this book. Remember, we just mentioned that we usually characterize oscillators by the sharpness of the resonance. The sharpness of the resonance is the ratio of the beats of the resonance and the frequency, and that the Q factor explains how fast energy decays in an oscillating system. It compares the frequency at which a system oscillates to the rate at which it dissipates its energy. What if there is another factor that could be added to the beats of the resonance and the frequency? This would be the angle of intersection of a wave with its axis, which would determine the effect of the energy of the wave on its environment. An example of that would be Earth. We mentioned that the Q of the rotation of the Earth is 107. It fulfills all of our requirements for resonance and oscillations. But we know as well that we can now observe the Earth's axis to be tilted 23.5 degrees from the plane of its orbit around the Sun. But this tilt changes. During a cycle that averages about 40,000 years, the tilt of the axis varies between 22.1 and 24.5 degrees. Because this tilt changes, the seasons as we know them can become exaggerated. More tilt means more severe seasons, warmer summers and colder winters. Less tilt means less severe seasons, cooler summers and milder winters. It's the cool summers that are thought to allow snow and ice to last from year to year in high latitudes, eventually building up into massive ice sheets. This is a direct observation that the angle is affecting the environment, and that the angle could actually be the main factor leading to this effect, not the Q factor. The thinking goes here that resonance changes the amplitude of the wave, which leads to changing the angle of intersection of a wave with its axis, leading to a different effect on the environment, field, or system. Here, we are discussing macroscopic planetary objects. Could this be applied to microscopic quantum objects? The answer is that we need to research it and test it, but in principle this could be applied to microscopic quantum objects. The angle could be affecting the system or the environment. Yet, to explore this a little bit more, let me tell you the electron story. Every electron could be considered as a little bar magnet with a north pole and a south pole. The magnetic moment for electrons is all the same length. Let's talk about the concept of preparing a state and detecting a state of that electron. Let's say we want to prepare this electron in a configuration where its magnetic moment is pointing vertically upward. How do we do it? We simply create a large magnetic field. For example, you bring a magnet, turn on some current, and make an electron magnet with a north pole and a south pole. The electron is supposed to be in the magnetic field, of course. We expect from our little bar magnet, the electron, that it will process around the magnetic field. But sooner or later, it will get rid of that precessional energy, as it will radiate electromagnetic radiation. It will radiate away its energy and come into the best energetic configuration pointing straight up, where the north pole of the electron is pointing towards the south pole of the magnet, and the south pole of the electron is pointing towards the north pole of the magnet. And if we do it with a big magnetic field, it will radiate the energy quickly and very quickly come to an equilibrium with the north pole of the electron pointing vertically upward. We could prepare the electron into a different configuration by rotating the magnetic poles at an angle. Now, we want to do a measurement to find out which direction the electron is pointing in. Now, we are sort of carrying a detection experiment. We can ask what the electron's angle is relative to the magnetic field. To answer that question, we do the same thing as we did to prepare the electron. We stick it into a large magnetic field and wait for it to radiate some radiations. If this was a classical setup, following the laws of classical physics, one measure of the angle would be how much radiation the electron emitted. For example, if it was almost perfectly upward to begin with, then we would expect that it only has a little bit of extra energy. Perfectly upward has the minimum energy. Rotate away a little bit. You give it a little bit of magnetic energy after letting it come to rest again. It does so by giving off that little bit of energy. If you were to go to a more extreme situation where you pointed the electron horizontally, then it would emit even more energy by the time it got vertical. Finally, if you point it straight down, it would emit the maximum amount of energy in the form of radiation. And then, you could at least measure the angle relative to the magnetic field by measuring how much radiation comes out, and the answer would be a nice continuous function of the angle of the electron, so you would measure the spin direction of the electron by letting it emit some radiation, and counting up the amount of radiation. It turns out that for a real electron, this is completely the wrong story. This is not the way it works. Something else happens, which illustrates the weirdness of the quantum world. It is not as we expected. It does not behave the way it should if it follows the laws of classical physics. First of all, no matter which way you prepare the electron, then you turn on the magnetic field, and one of two things happens. Only two things could happen. One is that it emits no photon, no electromagnetic radiation. The other is that it emits one photon of electromagnetic radiation of a very particular frequency that corresponds to the energy of jumping from down to up. It is almost as if the electron had only two possible configurations. There are only two states of an electron, either it is pointing up or it is pointing down. That is one of the puzzles of quantum mechanics. Of course, there is a whole lot of mathematics and quantum mechanics dealing with that. Yet, here we want to examine the effect of the angle of intersection of the wave with its axis. Let's consider the electron as a fluctuating wave. As mentioned above, it is expected that the angle of intersection of a wave with its axis is the main factor determining the effect of the wave on the environment, field, or system. Following this line of thought, electrons and other fundamental particles should not be changing amplitudes and should not be changing the angle of intersection of a wave with its axis. In other words, since they are fundamental, the update of their wave function should not result in changing the angle of the intersection of a wave with its axis. This is, again, of course, just an analogy aiming at examining the effect of the angle of intersection of a wave with its axis, and whether this idea could be applied to subatomic objects with quantum mechanical behavior, and it will require further scientific research and validation. Some of the proposed operations of the balancing force, or the B-force, one of the potential operations of the balancing force is to bring fields or systems to a balanced state. The balanced state does not mean a zero value or a ground state. It is a state where the system is in balance to achieve its targeted function within a specific space and time. The balanced state would be the resultant of the balancing force operation on any opera T, which could be a field of waves or just one single wave function. The balanced state is usually not zero, and it should be the value or set of values that achieve the required balance for the opera T or system in which the balancing force is operating in. A very basic example for that would be our straight line analogy, where the balancing force is operating in the straight line construction of reality to maintain its balanced state, which is expected to be a wavelength or a length of 10,500 in one dimension. A simple notation that could represent that, in a future video, we will explain how the higher dimension force, or the HD force, can operate on the straight line to reconstruct reality, and the information coded on the straight line into two dimensions. However, the operation of the HD force could be independent of the operation of the B force. They might not be affecting each other, as the B force is expected to be required to maintain the balance of the straight line, even if the HD force is operating on it.